Hi, today I'm going to talk about the solutions for the Atcoder Beginner Contest 408 Problems A to F. For problem A, the elder of Takahashi village falls asleep immediately. So if the time interval where they were tapped on the shoulder is greater than s plus 0.5 seconds, then the elder would fall asleep. And at this instant, the elder is currently awake after just being tapped on the shoulder, and we want to find after n taps, and each tap is ti seconds from now, and we want to find whether the elder is still awake after these n taps. And so we can do this by just checking each of the intervals to see if the interval is greater than s plus 0.5 seconds. So we can directly check the time interval between all the taps and between the first tap and our starting time. So let's look at the code. And here I first inputted the value for n and s, and then recorded the times where the elder is tapped on the shoulder, which is stored in this array T. And afterwards, I use index from 1 to n because this is easier for me to check the interval for the first tap, because I can always just do ti minus 1, and then for the first tap, this value would be 0, and then I don't have to check for use another if statement to check for the first tap. And so for this, we check if the interval is greater than s, and if it is, it means that the elder will fall asleep, and we print out no because this means that the elder will not be awake after n taps. And otherwise, we print out yes at the end. Let's look at problem B next. For problem B, we have an integer sequence A, and we want to output all the numbers in A in ascending order and remove all the duplicates in A. And since I'm using C++, we can directly do this through vectors. And let's look at my code for more details. I first inputted all the values for A in a vector by resizing the vector, and then I sorted the vector in ascending order. Afterwards, I used erase and unique. And let's look at what unique does. So unique is a function in C++ that sorts, it moves the elements so that all duplicate elements are at the back of the array. So for example, if the element begins with 1, 1, 2, 3, 4, 4, 5, then after unique, it will return the position where we need to start erasing from. So it will give 1, 2, 3, 4, 5, and then it will give the position where we can start erasing from, and we can use erase to erase from the last element to the end of the vector. And afterwards, this will give 1, 2, 3, 4, 5. So that's what I did, and then we can just directly use this function and erase from this point to the end of the vector, and this will give, since we already sorted the vector in ascending order, then this would directly give what we want as the answer, and then we can just output the information that the question wants. For problem C, in Atcoder kingdom, there are n castles with walls numbered from 1 to n, and there are also m turrets. And turret I guards castle walls numbered from L to R. And when a turret is destroyed, the castle walls that were guarded by the turret are no longer guarded. So we want to find the minimum number of turrets that need to be destroyed so that at least one castle wall is not guarded. And we can solve this by using prefix sum. So we can add 1, we can keep track of a variable sum, and then add 1 at position Li and subtract 1. Since this is inclusive, we can subtract 1 at position Ri plus 1. And then we can calculate the prefix sum, then find the minimum value over this region, the prefix sum would keep track of the number of turrets that guard the wall, and we can find the minimum value over all the prefix sum, which will be our answer. And if this is still not clear, we can look at an example. Let's look at the example for sample input 1. And in this case, I labeled the indexes for the walls, and then the red segments represent the walls that each turret guards. And what I just said is that we can keep track of a prefix sum called sum, and then for each range we can, for example, add 1 for this, signaling that this segment is being guarded, and then minus 1 here because the segment ended at 6. And we can do this for all the other segments, add 1 here and subtract 1 here. And afterwards, we can calculate the prefix sum for this array, which will give us And looking at this, and with the segments here, we know that this just represents the number of turrets that are guarding the walls at each index. So corresponding to the number of lines, we know that here there's only 1 line and corresponds with 1. And here there starts to be 2 lines, and this corresponds to 2. And in the region 5, there's 3 lines, and this corresponds with 3, and so on. So we can do this for all of the walls in O(n) time, and then we can find the minimum value from 1 to n in this range, which will represent the minimum number of turrets that we need to remove. And next, we can look at the code. So sum is the prefix sum that I mentioned, and then for this, this is adding the values just like I did in the example, where I add 1 in L and subtract 1 in R plus 1. And afterwards, we calculate the prefix sum. And answer keeps track of the minimum prefix sum. And this will just be the minimum number of turrets that we need to remove, and also will be our answer. Next, we look at problem D. For problem D, we have a string of length n that consists of zeros and ones, and we can perform the operation several times, which is to flip 0 from 1 or 1 to 0. And we need to perform these operations so that the ones in S form at most one interval, and we want to find the minimum number of operations to achieve this. So let's look at a sample input. And for sample input 1, the minimum operation is 1 because we can flip the first 1 to 0. And this will give only one region here where the values are 1. And there's no need to perform any operations on these because the ones already form only one interval. And this one forms no intervals and all satisfies the problem's requirements. Let's look at how to solve this problem. And so our goal is to find L and R so that there are L's in there are ones in the region L to R, and then otherwise in the other regions they're all 0. So we want to perform operations to make it so that there's this kind of intervals. And so since we want the values inside L to R to all be 1, our operation would be to flip all the ones outside of L and R to 0, and all zeros outside in the range L and R to 1. So this visualizes what we want to make, so which is a range from L to R with all ones and all other locations with all zeros. So we want to flip all the ones here and here to 0 and flip all the zeros in this segment to ones. And our goal is to find L and R that minimizes these operations. And the operations that we need would be to flip the ones from 0 to L all to 0, and the ones from R to N all to 0. So this part, and then we want to flip all the zeros in L and R to ones. And this part would be equal to the total number of ones in the entire string subtracted by the number of ones in the range L to R. And this part, the number of zeros in L to R would correspond to the length of the interval subtracted by the number of ones in that interval. And rearranging this, we will get the length of the interval plus the total number of ones subtracted by 2 times the number of ones in the interval L to R. And so what we want to do is to minimize the length subtracted by 2 times the number of ones in the range L to R, because total ones in the string is constant. And if we want to minimize this value, this is equal to maximizing the number of ones 2 times the number of ones in L to R subtracted by the length. And to do so, we can keep track of another array called B. And so if Si is equal to 1, B will also be equal to 1, because if Si is equal to 1, then this would contribute 2 times 1, and then we subtract 1 because it also contributes 1 to the length. So this will equal 1. So B will be 1. And if Si is equal to 0, then Bi will be negative 1, because this is 2 times 0 minus 1. And so B keeps track of the contribution of each index to this value that we want to maximize. And since we want to maximize B, we've transformed the question to a question that we want to maximize B for some subarray and some interval. So the problem is converted to finding a subarray in B with the greatest sum. And we can do this by dynamic programming. So we can keep track of dpi, where the dp represents the maximum sum subarray that ends in ai. So the transformation, the dp transition would be dpi would be the maximum of dpi minus 1 plus ai and ai. And this is because ai can be added to the previous maximum sum subarray that ends in ai minus 1, or ai could be an entirely new subarray. So there's 2 possibilities for subarrays that end in ai. And then afterwards, the answer would be the maximum of all the dp's, because this would consider all subarrays that end in 0 and then end in n minus 1. And next, if this is clear, that we can look at my code. So I first inputted all the values for S, and I didn't use B here, but in my code, A is equal to B in my previous explanation. And so for this, if Si is equal to 0, I set ai to negative 1, as I previously mentioned. And here, if Si is equal to 1, I set ai to 1. And I increase the total, which is still needed, because in the end, our answer is total minus m, since we want to maximize m. And m sum is the value for dp that I previously mentioned. And this is the initial value for m sum would be the maximum of 0 and a0. And m just keeps track of our answer, which, as I just mentioned, would be the maximum of all the values from in m sum from 0 to s dot length. And this is just the dp transition that I mentioned previously. And this part is to calculate the maximum value, and it finds all the maximum sum for each value in the dp. And this part outputs the answer, because m is the value for m is the maximum value that we try to maximize when in what I previously explained, and it is 2 times the number of ones in the range L to R subtracted by the length of that range. And then in our previous calculation here, our calculation is that we also need to add total ones here. So this is what we maximized, and this is equal to m in my code. So our answer would be total ones subtracted by m, because m is this value. Next, we can move on to problem E. And for problem E, we have a graph with n vertices and m edges. And the edges are undirected. So these edges connect vertices u and v and has a label of w. And we want to find from all the paths from vertex 1 to vertex n, we want to find the minimum possible value of the bitwise OR of all labels on the edges included in the path. So bitwise OR is just that for each bit, we look at each bit separately. And for each bit, if one of the values is 1, then the bitwise OR value will be 1. So in this example, the bitwise OR will be 111 because this value is 1, so this bit will be 1. And these 2 bits are also 1, so these 2 bits will also be 1. And since we want to minimize the bitwise OR, we can loop through the values from the most significant bit, which is here, to the least significant bit. So what we can do is we can start from, since the range for the values is only 30 bits, so we can start from the most significant bit, which is from 29 back to 0. And since each bit in the bitwise OR is treated separately, so we can also keep track of each of the bits separately. So from the most significant bit, we can keep track of a variable answer, which keeps track of the current minimum bitwise OR, which will later be our answer. And we can initialize answer first to 2 to the 30 minus 1, and this represented in binary is just 30 bits that are all ones. And this is because initially we don't know which bits we can have, which bits we can have 0. So initially we set all the bits to 1. And afterwards, for each bit, we loop from the most significant bit to the least. We can check if there's a path from 1 to n that has a bitwise OR of 0. So we can do a DFS from 1, and then for each edge, when we want to check if we can move through that edge, if we can move across the edge, if it has 0 for the current bit that we're looking at. So when we do the DFS, we need to record which bit we're currently on, so which bit we're currently looking at. And then the edge also has to have 0 for all bits that we already checked and already have answer equal to 0 for that bit. So this may be confusing, and we can look at an example to make this more clear. So for example, if we are currently on this bit and we've already updated answer so that these two bits are all 0, then when we DFS from 1 for this bit, we can move across the edge if the weight or the label for this edge is not 1 for these 3 positions. This is because we want to check if the current position may have a path that has a bitwise OR of 0. And so we don't want this position to be 1 because otherwise the bitwise OR cannot be 0. And however, we need to ensure that our previous results, because previously we looped from this bit all the way till here. So we loop from the most significant bit to here. And then, so these bits are more important because they contribute a larger value to the answer. So we cannot make these bits 1 since we already previously checked that there exists paths that make these bits 0. So if we want to cross the edge, then these bits also need to be 0. So for each edge, we need to check all these values that the current bit that we're looking at is 1, and all previous bits that we already checked for and can be 0 also needs to be 0. So these bits all can't be 1. And later, if it's possible to reach n after these DFS, so for this bit, we perform the DFS as mentioned here, and for each time we check if it can cross the edge for all the edge that is connected to the current vertex. And so if it's possible to reach n at the end, then this means that there is a path that satisfies the conditions. And then this means that we can change the current bit in the answer to 0. So for example, if we're currently on this bit and then afterwards we find out that we can reach n, then we can change this bit to 0. And after looping through all the values from the highest bit to the lowest bit, answer will store the best possible answer. And for my code, I used a vector of pairs to store the graph, and I initialized the answer to 2 to the power of 30 minus 1. And then this I looped from the highest bit 29 to 0. And for each, I performed a DFS by first setting visited, which visited is an array that will keep track of whether the current vertex is visited in this current loop that we're checking for. So I reinitialized visited to false, and then I performed DFS starting from 1 and recording the current bit that I'm looking at. So for this part is my DFS, and then this part is checking whether the current edge can be passed through. So this is what I mentioned about we need to check whether it satisfies all previous results that we already have. So for bits that are greater than the current bit I stored as D. And for bits that are greater than the current bit, if the answer is not 1, then it means that there was previously a path that can make the bitwise OR 0. So the edge can also not be 0. So possible stores whether we can pass this edge. And then this part is that the current value for this bit can also not be 1. So if it's possible, we can pass through this edge and continue the DFS, and each time we update the visited array. Afterwards, we check if we can visit n. So if it's possible to reach n, that means that there is some path from 1 to n that satisfies all the conditions, and we can change this current bit in answer to 0. For problem F, there are n scaffolds numbered from 1 to n arranged in a line, and the height of scaffold I is hi. And Takahashi decides to play a game of moving on the scaffolds. So he initially can choose a random scaffold to stand on, and then afterwards he has some conditions to move to another point. So he can move to another point if the point is within a distance of r from his current point, and if the point has a height of at least less than d from his current height. So we want to find the maximum number of moves he can make while he repeats these moves. So we can look at a sample. So for this sample, he can start from scaffold 1, and then he can move to scaffold 2, because this is within a distance of 1 from his initial position, and then it's at least 2 smaller than its original value. And afterwards, he can move to scaffold 3, which has a value of 1. And this is a total of 2 moves. So the answer is 2. We can solve this problem by keeping track of a dp, where dpi represents the maximum number of moves if we start at I. And then, since we can only move from a higher value of h to a lower value, the dp would transition from lower values of h to higher values. So we want to update dp in increasing order of height. And so we want to sort the height array. And however, if we update the dp, we will also need to check all values in the range I minus r to I plus r. And this will take too much time, since this will add a time complexity of OR to the solution. And then we don't want this because this will exceed the time limit. However, we notice that since our dp will transition from the maximum value in this range, then we can use a segment tree, because point update segment trees can quickly find maximum in a specific range. So we can use these segment trees to store our dp, and then afterwards, for index I, we can store a array index where index I represents the first value j, where the height j is greater than or equal to height I plus d. So this is one of the constraints of the problem. And then we can store another array, value I, which will store the values that need to be updated. And we do this because we need to update the value for j when we reach the index I. because otherwise it will include values that doesn't satisfy this condition. So if we update the value for j and store it in value when we reach index I in our loop, then this can ensure that all current values that have already been updated in the DP satisfy the condition that the height has a difference of at least d. Then we can store this value in the array value to be updated later when we reach that index. And so what we want to do is we want to loop through the index I from 0 to n, and then for each index we update dpi to value I, and then we update the value for the index I, which is the next position that has a height difference of at least d. And the answer would be the maximum value for all these DPs. And if this is still not clear, we can look at this example. So we would start with increasing values for height. So we would start with this value. And initially, the DP for these value would be some negative number that's very large, and then we would initialize this value to 0. And this is because this is the first value, and then the number of moves that we can make if we start here is just 0. And then afterwards we can move on to the next value, which is 2. And in this case the value is also 0 because in the range of 1, a distance of 1 from this point, there are no values that have already been updated and satisfy the constraints. So this is not possible. And afterwards we move on to 3. And this would get 1 because it can transition from here. It satisfies the condition that the difference between them is at least 2 and the distance is 1. Then we move on to the next value, which is 4, and this will give a value of 1 because the distance between these is at least 2, the difference, and then the distance is only 1. And next we move on to the last value, which is 5, and this would give us 2 because it can transition from here. And in the end our result would be 2, which is the maximum in the DP. And let's look at another example to make this clear. We would start from here, and this would be 0. Afterwards, what I just did is not what the code would do exactly, because the code, so when the code will actually loop through these here, and then when we reach this index, I would store the value for this, since this is index 3 would equal to 6. So I would store value 6 for this, and I will update the value. But when I'm doing the example, I just directly write it on here. So this is what you would do in the code, which is store this in a value, and then afterwards when we loop through, we will assign dpi to value I when we loop through these indexes, and then in the end find the maximum. But just to make giving the example easier, I will do this, and then so this afterwards we move on to 2, and this will give 0 because there is no other moves that can be made. Next we move on to 3, and this also gives 0 because in the range of a distance of 2, there is no steps. Then we move on to 4, and this also gives 0. Because in this distance, there is nothing that can be updated. Next, for 5, we can update this because this can be updated from here. It is 4 at least, so at least 3 away from 1, and then the distance is only 2. So this can be changed to 1. And we move on to 6. And this can be updated from here. So this is also 1. And we can continue this process until we update all the values until 13. And now we can look at the code. So this part is my segment tree. And then afterwards, I first sort h, and I store h in a pair because then I can store the index for h. And so this stores the height, and this stores my index. And so I will still have my index after I sort it. So this part I'm finding the index, which is I use lower bound to find the first position that has a value greater than or equal to the height plus d. So this part is the loop that I mentioned. So we loop through the values here, and then for each we update the value, the current index, to the value that we already stored. So if we didn't store anything, if we didn't update it, it will automatically be 0, which is what we want. And afterwards we find this, for this query, we query from the index, the distance r left and right away from our current position. So this finds the maximum value of dp in this position. And then we update this for value, which we will update to dp later when we loop through that index. And so if index I is equal to n, then that means that there is no value that's equal to hi plus d. Then for this case, we just have to update the value for dp, and there's no need to update the value for the value of a. So we can directly continue. And afterwards, in the end, the answer would be the maximum of the dp. So we can just query in the segment tree, which will give us the maximum. And this will just be the answer. And thanks for listening.